Hello, my name is Joachim Pieprek. I will be talking about energy efficiency analysis of gallium nitride-based superluminescent diodes, so-called SLEDs. And these SLEDs have a number of potentially very interesting applications, for instance, in augmented reality displays, little mini projectors that you can wear in your headset or in cars or other applications. And that was shown last year at our NUSOD conference by Nikolai Matuszek and got me quite excited about these tiny devices. And the most popular devices based on gallium nitride are LEDs, which are part of the white light sources that we see everywhere now. And these LEDs emit light or photons spontaneously. These photons are not correlated, they go in all directions. SLEDs, on the other hand, bundle these photons inside an internal waveguide, so the photons can generate new photons by stimulated emission, and we get light as so-called amplified spontaneous emission. And the next step would be to put reflective interfaces on both ends of these waveguides, and then the light power inside the device can build up and become very strong until we reach lasing threshold. And then we have stimulated emission in a very narrow lasing beams. So the SLEDs are in between LEDs and lasers. And what puzzled me when looking into these devices was the low energy efficiency, or so-called wall plug efficiency, which is only 10%. That means that 90% of the electrical energy that we put into these little devices is lost. 90% is gone. Only 10% comes out as light. The LEDs are much better. The 80% comes out as light. That is why we use these devices in lighting applications. And lasers are also somewhat better and emit about 40% of the energy as light. So I try to investigate that mystery by device simulation using the Pix3D software from Crosslight Software. And this software combines the drift diffusion model for electrons and holes with models for photon generation inside the active layers, the quantum wells, and as well as models for the wave guiding of these photons internally. And all this is coupled to the heat flux equation, so the internal heating of the device is also considered. In this way, by integrating all these different device physics into one simulation, we can achieve realistic results and compare with actual measurements. And that is what I did a few years ago for laser diodes. At that time, I analyzed a laser made by Panasonic, which at the time had the highest output power of any gallium nitride-based laser, 7.2 watts, and a wall plug efficiency of 39%. But still, even for that laser, we wanted to know why is the efficiency only 39%, because we always want more efficiency. And some of these results are shown here. They were published in the Journal of Quantum Electronics in 2017. On the left, you see the refractive index profile, the optical wave profile in blue, and the dashed green line is a local absorption, mainly free carrier absorption inside the device. And it took quite some effort to fine-tune all the parameters inside the simulation so that we see a good agreement between the measurement shown as dots here and the simulation in the power versus current characteristics. And after achieving this agreement, we can now play with the internal physics in the simulation and, for instance, turn off the absorption or turn off the Auger recombination and see what impact that has on the laser diode. So that was quite educating. And now I will do the same thing for the SLED. And as I mentioned in the beginning, SLEDs are very similar to laser diodes. So we can use the same layer structure, the same material parameters, same cavity length, same ridge width, same thermal resistance, same contact resistance. So the only thing that is changed in the laser simulation is the front facet reflectivity. When we set that reflectivity to 0, then the photons don't come back from that. Facets are not reflected back inside, and we don't see a lasing threshold. And in other words, that is then a superluminescent diode, not a laser. And here are the results shown in comparison between the SLED and the laser. The dots are the laser measurements again, and the blue dashed line was the laser power curve that I already showed. And when we now turn to the SLED, we see the power drops dramatically. The power is much lower. That is what we know from experiments. The bias, the voltage inside the device doesn't change that much, only a little bit, because we have the same device structure, same electrical resistance. But since there is less light coming out, more power stays inside. So we have a stronger self-heating with the SLED. So these devices get quite hot when we put in a lot of current, and the SLED gets even hotter than the laser diode. And we can now analyze the efficiency, the wall plug efficiency, just by dividing the optical output power by the electrical input power. And after some manipulation of the formulas, we can separate this efficiency into an electrical efficiency, ELE, which is shown as green lines here. So it's almost the same for both devices. It practically represents the electrical resistance, which is the same for both. And this ELE already reduces the efficiency down to 50%, down to 0.5. So this is a very strong influence that we see in both devices. So electrical resistance has a strong influence of the on the efficiency, but it doesn't, it's not different for the SLED. Then the next part here is the EXE, that is a photon extraction efficiency, which in both cases is relatively high. So it doesn't really limit the overall efficiency. But then the third element, the IQE, internal quantum efficiency, that sees a strong drop. So from the laser that has more than 70% down to the SLED that has maybe 20%. And all three together then gives the wall plug efficiency, which is for the laser in agreement with the laser measurement, but much smaller for the SLED, around 10%. So the main difference between both device types comes from the internal quantum efficiency, which stands for internal carrier losses or current losses. So we have to look into the current contributions in our simulation. And what we usually want and expect is that most of the internal current, the current that we inject into the device, is supporting photon emission. So, and that happens for the laser here. The blue dotted or dashed line is the laser light that comes out. It's stronger than any other dashed line here. But for the SLED, the light that is generated actually consumes less current than this red line, which stands for Auger recombination. So most of the current in an SLED goes into a carrier loss mechanism that is well known for these gallium-nitride-based devices, and also for other devices. Auger recombination often consumes most of the current, in at least at the laser threshold, that is well known. And it is a process that goes proportional to the third power of the carrier density. And so it very much depends on the carrier density in the active layers. All the other carrier loss mechanisms, spontaneous emission, electron leakage, defect recombination, are much weaker. This is a logarithmic scale, so we really only worry about Auger recombination here and the carrier density. So let's look at the carrier density. In our simulation, average quantum well carrier density over current. And for the laser, we actually expect a clamped carrier density, a constant carrier density. That is a common wisdom, but it's only true if the temperature stays constant. But we have here a strong self-heating. We already saw that. So to maintain lasing, the carrier density has to rise inside the quantum wells to maintain the threshold gain in the laser. But the SLED is much worse. In the SLED, the carrier density is higher and also rises in a stronger way, and that causes then these Auger recombination losses. So in summary, we can say that self-heating is a strong reason for the limited energy efficiency in SLEDs and also the large electrical resistance. Sorry. But these two things also happen with lasers. The one thing that is different in SLEDs is the carrier density in the quantum wells, and that is higher and rises stronger, and that's why it causes stronger energy losses, and that's why the energy efficiency of SLEDs is so much lower than with laser diodes. If you're interested in more details of this study, then you can look up these two papers that I have listed here at the end. Thank you very much for your attention.